Hello, dear students. We will have for each 3 or 4 lectures, we will have a revision lecture, and this is a revision lecture because I know that if we just rely on the PowerPoint, you cannot grasp all the ideas perfectly like those mentioned on the board directly. So we will just recap the last 3 lectures in this quick lecture, and we will rely exclusively on the whiteboard. So if you remember that chromatography, as we said, it is simply from color and analysis. So Tsuit in 1906 relies on column chromatography to separate the plant extract. In order to understand the mechanism of separation without any ambiguity, we will just draw simply here that resin contains pores or sometimes tunnels. So these pores allow small molecules to go through them, okay, but not large molecules. Okay, so some of these molecules will go directly through interparticulate pathway. As we see here, we have particles, so the movement should be interparticulate and intraparticulate. So the movement for small molecules will be both inter and intraparticulate, and this movement will take longer time from the small molecules, whereas large molecules are all just have one pathway, which is interparticulate pathway. So the large molecules will go first. After a certain period of time, the small molecules will be eluted. So if we monitor by certain detection instruments or tools, we will detect that the large molecule will go first, then the small molecule will go behind the large one. The area under the curve here of detection will rely on two things. First of all, if we are, for example, detect the elution by UV, it will rely on the light absorbance for the molecule. Okay, if it contains good chromophore, then the molecule will absorb electron better than those which lacks chromophore. The other thing, that area under the curve relies on the quantity of the material. So if we have abundant quantity of small molecules, the area under the curve will be larger than those for big molecules, or vice versa, relying on, as we said, on two factors: the chromophoric part, the absorptivity of the molecule, and the quantity of the molecule. Okay, and we call this mechanism, if you remember, size exclusion. Okay, size exclusion mechanism, and also it has other names like gel permeation. Okay, and also we can call this mechanism molecular sieve mechanism. Okay, and if you remember, we discussed these things thoroughly in the recorded lectures in YouTube. We mentioned that other mechanisms will be elaborated, but not during these lectures. Later on, we will discuss the other mechanisms of chromatography thoroughly, if God willing. And we start also to talk about the techniques of chromatography, and we start to talk about paper and thin layer chromatography. Now, thin layer chromatography, from its name, it is simply a layer of silica, usually silica or any other derivative of silica, and in this case, this layer covers a glass sheet or aluminum sheet. because we just use thin layer from silica, we call it thin layer chromatography. Just we have usually zero point 0.2 millimeter or sometimes 0.5 millimeters in thickness of the stationary phase. That's why we call it TLC. Okay, the same thing that the concept might be applicable if we use a paper sheet, and this paper usually from cellulose like filter paper. Okay, uh, in order to understand the concept we discussed about the use of TLC in the real application, one of the application we said we can use TLC or paper chromatography for monitoring chemical reactions. Now, we will take a case in order to understand what do we mean exactly. For example, if we have a reaction and the reaction should gives the product C, so we simply take a sheet or paper filter, and we apply in this case the starting material as reference material A, B here, then X, assuming that X should contain C. But this is a reaction vessel, and we take a sample from the reaction vessel, and we have to emphasize that the quantity of the sample should be the least possible quantity, and in this case we just spot this quantity from the reaction vessel, and we will because in this case, in order to monitor the reaction, we need to take these small quantities for each period of time. So for example, in our elaborated example we mentioned previously, that in each 30 minutes we can take just a sample, a tiny sample, and to measure the content of the sample. So after applying thin layer chromatography in a jar, we close the jar and we fill it with mobile phase. The mobile phase should not exceed the line of the application. After a certain period of time, the mobile phase will reach a point, and we can dry the plate in order to see now what happened for the analytes. Assuming that A migrate to this point, B to this point. Now, if the mixture from the reaction vessel just gave two spots, this means that we just have A, which is co-aligned with the reference material here, and B. So there is no indication for the product. Assuming that we increase the time for certain time increment, and we obtain a new spot. This means that this new spot most probably for what? For the product. But the reaction is still proceeding, because the spot for A and B should still appear. Now, if one of them after a certain period of time disappeared, this means the reaction is finished, because we consume totally the compound B, although we have A in excess and also we have the product. Now, if more time is given to the reaction vessel, you might see other spots. These spots might be for byproduct or degradation product for the either reacting material or the product. So it's better to stick with the time mentioned previously which just give you complete reaction without serious degradation products or byproducts. Now, this is one of the useful application of TLC. We have many applications, and we will discuss also another application for TLC. If we are interested, for example, in limit tests that paracetamol should be intact, and you know that paracetamol gives para-aminophenol as byproduct and degradation product with time being. Now, para-aminophenol is hazardous, toxic. So we have to have para-aminophenol in very low amount for certain limit in paracetamol. For example, if we have paracetamol suspension, okay, we can dilute this suspension for a certain extent, and here we have paracetamol, okay, suspension. Now here we have paracetamol as reference material, as standard, and thirdly we have what? We have para-aminophenol. Now para-aminophenol is the degradation product. So in order to see if we have para-aminophenol in paracetamol suspension or not, we have the standard material here. Now, assuming that we have a spot here for para-aminophenol, here we have for paracetamol we have a spot here, whereas paracetamol gives us just one spot. Now, this one spot just parallel with paracetamol, so we have nothing from para-aminophenol. Sometimes we have para-aminophenol, but in concentration less than the limit test. The limit test here for assuming we have 0.1%. So this is more faint than the spot here. So the byproduct or the resident product of para-aminophenol doesn't exceed 0.1%, and assuming that 0.1% is the allowable limit, so we can pass paracetamol. But if the spot more intense than the limit, the maximum limit, allowable limit, here 0.1%, in this case we should reject paracetamol suspension, and we shouldn't allow the patient to use this kind of product. Okay, so this is just recap for the things we mentioned so far, and we will discuss after each 3 or 4 lectures. We will discuss the major theme of the lectures by using whiteboard, and the normal lectures, as I said, they will be just PowerPoint, and this PowerPoint will be reported in YouTube.